Okay, it is almost never okay to prove a statement with just one example. Now that's very important. Okay, certainly none of the statements proved above can be proved through just giving an example. This is because in each of the cases we are trying to prove that something holds for all integers. We claim that n squared being even implies that n is even, no matter what integer n we pick. Okay, showing that this works for 4 is simply just not enough. So let's see what he suggests. He says this cannot be stressed enough. If you are trying to prove a statement of the form for all x then p of x, you absolutely cannot prove this with an example. Remember, this is a universal statement. It's making a statement about all the x's. But for existential statements, you can prove it by example. If we want to prove that there's an integer n, such that n squared minus n plus 41 is not prime, all we need to do is find one such an integer for which it is not true. Now folks, if you look at that equation, read it again. If we want to prove that there is an integer n such that that is not prime, okay, you can go and you can start filling out a table. Now if you start filling out that table with examples, you see that indeed, we've gone up to 7 here, that all those numbers are indeed prime. Just look at the equation though. If n was 41, then minus 41 plus 41 is 0, and n squared will be 41 squared, which has 3 factors. It has 1, it has 41, and 41. Okay, so that is not a prime number, and hence you've proved it by providing a counterexample to what they were looking for. Okay, so let's have a look at more examples. Okay, we're looking at an example that asks us, is the converse of the following statement true? That for all integers, notice this is universal for all integers a and b, if, conditional, a and b is odd, then a is odd or b is odd. Okay, we want to prove this statement. We want to prove that the converse, we don't want to prove this statement, we want to prove if the converse of the statement is true. Okay, so let us word the converse. The converse will be that for all integers a and for all integers a and b, if a is odd or b is odd, okay, if a is odd or b is odd, then a plus b is odd. That is what we want to prove. Okay, now this is false. Why? How do we prove that it's false? We need to prove the negation of the converse. The negation of the converse is what we need here. So let's translate what we've written here into symbols. Okay, for all a and for all b's, the following is true. If a is odd or b is odd, then the sum of a plus b will be odd. So we're representing odd with the letter O. Okay, so this is what this statement is saying. We want to prove the negation of this statement. Okay, so if we go for the negation, it means that we need to prove the negation of what we've got over here. Okay, now let's see how that works. To prove the negation of this, so if we want to work with a negation of for all A and for all B, if A is odd or B is odd, then the whole sum A plus B will be odd. We want to prove that negation. Okay, so if we use the rules from our previous sections that we've learned, we know that if we bring a negation in over a universal statement, the for all, it turns to an existential statement. So this would change to there is an A and there is a value of B, so that if A is odd or B is odd, okay, and not odd for A plus B. Now remember, what are we doing? We are changing a conditional statement into a conjunction. Okay, remember what we learned earlier on? We learned in our previous chapter that this is possible, and it was emphasized that implications are disjunctions. For instance, we worked with that. We've worked with a double negation. We've worked with a negation of an implication and how we negate this implication to become a conjunction. So the negation of an implication was a conjunction, which is over there. Okay, so let's continue to discuss this. As the negation passed over the quantifiers, they changed from universal quantifiers to existential. We then need to take the negation of an implication, which we did. We took the negation of an implication and it turned into a conjunction. Now we know that to prove the converse is false, we need to find integers A and B, so that A is odd or B is odd, but A plus B is not odd. So in other words, it is even. Now let's think about this. We can have A odd or B odd or both. That's what the or means. It can be one or the other or both. Okay, so if we look at the number 1 for A and we look at the number 3 for B, both of them are odd numbers. Then what is A plus B? A plus B is 1 plus 3, which is 4. So this was odd, this was odd, this is thus even. Okay. Both of those are odd, but for the sum is not odd. Okay, so have we found an example that proves that this is true? Indeed. Okay, so what we wanted to show, the converse is indeed true. Okay, folks, I hope that gives you something good to think about.